At the last session of the evening, this will be a full 25-minute session, so it's going to go a little past 1900 hours. I'm pleased to introduce Roger Powell from Citrix, who will be talking about things in the Zen project. Roger?
Hi, my name is Roger. I work for Citrix on the open source Zen project mostly. I'm also a FreeBSD developer, and I also do a little bit of Linux and QEMU work when needed. But recently my main focus has been Zen, and I've been working on something that we called PVH, which is a new virtualization mode for Zen that we plan to use for both guest and host. And I'm here today to introduce the differences between PV and PVH Dom0 and how that's going to change the Zen ecosystem. I usually start with a brief description of a typical Zen domain. Yeah, well, in any case, here we have the hardware that contains the CPU, the memory management unit, all your PC devices, everything is right there. Then we have Zen on top of that hardware. Zen basically takes control over the CPU, the MMIU, some timers, the local APICs, and that's mostly all. It doesn't have drivers for PC devices. It doesn't have drivers for anything else, basically, for your disk. It doesn't have any of those drivers. All those drivers are inside of what we call the control domain. That's the first guest that's launched by Zen, and it can either be Linux, FreeBSD, or NetBSD, basically. And usually inside of that domain, we have all the drivers for the different devices on the system, the PC devices, the network cards, the disk, everything is usually inside of the control domain. And then on top of the control domain, I put some tasks that you usually have running on your control domain, like syslog, nixterm, xorg, yeah, whatever you want. And here I've added two guests also. As we can see in this picture, the guests inside of Zen are on par with the control domain. They more or less share the same interface, and even the control domain is just a guest from Zen point of view. Here, on the other hand, I have a description of what would usually be a type 2 hypervisor. That would be KVM, Beehive, VirtualBox. All those type 2 hypervisors share more or less the same design, which means that you have the hardware, and then on top of the hardware, you have your operating system, either Linux or Windows or Mac OS or whatever, and then there's a small module inside of your operating system. That's the hypervisor that takes care of controlling the hypervisor functions on the CPU. And here, for example, we can see that we have some task on what would be your host, your operating system. We have, well, I place the same task basically, and we also have some guests. And I would like to notice the difference from the picture before, because here we can see that the guests share the same scheduler, for example, with the applications that are running on the host OS. That's not something that happens with type 1 hypervisors, because it's completely isolated, and the scheduler is only designed to run VMs, not to run tasks. And here we can see that the guests actually compete for resources with the tasks that you have running on your host. So yeah, now I would like to speak a little bit about the current Dom0 interface and the limitations that we have with that interface. This interface was designed a very long time ago, in the 90s. So it's, well, a little bit different from what we would do it now. We've been using that interface for a long time, but we reached a point where I think we need a change, and we need to improve the interface that we provide to Dom0 in order to make it easier. So one of the key differences of the Zen interface is that when Zen was designed, there was no hardware virtualization extensions, which means that you could not virtualize the CPU. You didn't have any support from the CPU in order to do virtualization. That means that when Zen takes over the memory management unit, we have to provide a different interface for OSs in order to interact with that memory management unit. So that's one thing that's different on Zen, and it's very intrusive because all the architectures have only one interface to the memory management unit, and Zen was basically introducing another interface to the memory management unit on its 86. That's something that doesn't happen anywhere, so it was very intrusive in the terms of the modifications that you need to perform to the operating system that want to run on top of Zen. The CPU handling is done also completely different. The setup and the delivery of interrupts is also very, very different from bare metal. That's mainly because on PV guest, on the current Dom0 interface, we don't provide a local APIC to the Dom0, so basically we have to use another way to deliver interrupts. And finally, the ACPI tables are also quite different. Well, not really different, but the tables that we provide to Dom0 are not very good in regards of the actual description of the system. I will go a little bit into this. So yeah, as I said before, the MMIU is different on PV guest because basically we have to provide a set of hypercodes that the guest can use in order to interact with the memory management unit, and that's different from what's done on bare metal, that you just have certain instructions that are used in order to interact with the memory management unit. This code, as I said, is very intrusive because you have to modify core parts of the OS in order to introduce all this Zen-specific code. It's also limited to 4 KB pages only. You cannot use 2 megabyte pages or gigabyte pages, so that's quite a problem related to performance, especially now that we have systems with a lot of memory. And it involves using hypercodes in order to set up your page table. So it means that every time you want to do a fork of a task or something like that, you have to issue hypercodes to the hypervisor, and the hypervisor has to create the page tables for you, and it's very intrusive. And finally, also, PV guests cannot use what's called privilege instructions, so they have to resort to the hypervisor in order to execute them on behalf of the guest. This also involves using hypercodes. Then, related to CPU handling, there are quite a lot of things that are different comparing Zen to bare metal. On bare metal, the boot time CPU discovery is done using a table on ACPI that's called MADT. On a PV guest, it's done using hypercodes. It means that you have to modify the boot code of the very early code of an OS in order to use hypercodes instead of ACPI in order to discover the CPUs. And again, this is very intrusive. Also, the bring up of the secondary CPUs on native, it's done using the local APIC. You have to send a set of APIs in order to wake up secondary CPUs. And on PV, it's done using hypercodes. And also the hot block of CPUs on native, it's done using what's called a general purpose event block. That's something that came from ACPI, and something that's also part of ACPI that are the processor objects. So you basically receive an event from ACPI, and then you scan, well, scan your processor objects and detect that new objects are online. Again, on Zen, this is done completely different, and we use something that's called ZenStore, which is like a database that's shared between the guest and Zen, and it's used to pass information between the hypervisor and Zen and between different guests running on the same system. The setup and delivery of interrupts is also quite different on native. On native, you basically receive all the interrupts from the local APIC, and then the local APIC injects those interrupts into the CPU. And there are mainly 2 different kinds of interrupts on each 86. The ones are called the legacy PCI interrupts. Those are implemented as sideband signals that go into the local APIC, and then the local APIC injects them into the, go into the IO APIC, and the IO APIC injects them into the local APIC. And we also have a newer kind of interrupts that's called MSI or MSIX that are implemented using in-band signals and are delivered directly to the local APIC. This is done by programming a certain address on your PC device, and the PC device will write to this address when it has to trigger an interrupt, and this address is trapped by the local APIC, and it injects the interrupt into the CPU. The configuration of interrupts on PC systems is also done from the PC configuration space, which is a set of IO ports that you use in order to interact with your devices, or a memory area that you also use in order to interact with those devices. And yeah, on PV, this is quite different because, as I said before, PV don't have any kind of APIC, so basically we cannot inject interrupts using an APIC at all. And we have to inject interrupts into the guest using another mechanism that's called event channels. Event channels are something specific to Zen and are called a para-virtualized interface that's used by Zen in order to inject events into the guest. This again implies modifying quite a lot of the code in guest OSs in order to be able to implement this new interrupt interface that's only used by Zen. And this also has the problem that it creates a lot of maintainership burden inside of OSs, because you have to introduce a lot of code and you also have to maintain this code. And to be honest, this code is quite critical. I mean, the interrupt paths are not something that you really want to be modifying in any OS. And finally, as we don't have any emulated PC configuration space on PBGuess, we also have to set up interrupts using hypercalls, which means that, well, this whole interface is very different from native, and it's not a trivial amount of code. So here I have the picture of what would be an interrupt injection to a PBGuess. You have your physical device. This injects an interrupt into the APIC. That's the physical APIC, and that's controlled by Zen. Zen receives this interrupt and injects the interrupt into the guest using the event channels, and the guest finally receives the interrupt. And finally, one of the things that is also different on a Dom0 compared to bare metal is the ACPI tables. I would like to speak a little bit before about the ACPI tables. There are mainly two different kinds of ACPI tables. One of them are called the static tables that are used on boot and are very simple tables in memory that can be mapped to a C structure. So they don't contain anything very complicated. It's just a static information that you can use during boot. They are very easy to parse, they are very easy to modify, they don't contain anything weird in general, but these tables are only meant to be used for very early boot information, and most of the real information on an ACPI system is provided using what's called dynamic tables. These tables are written in a language that's called ACPI matching language. This language requires you to have a parser inside of the kernel in order to be able to discover these tables, and on these tables you actually find also static information about devices, but they also contain methods that you can actually execute. So they are a little bit more complex, and this is where, for example, on these dynamic tables is where you find the information about all your PC devices, so most of the information on the system actually came from these tables. And one of the problems is that on a traditional Dom0, all these tables are passed as is to the guest, which means that the information received by Dom0 is not the information that it should have received. For example, you can limit Dom0 to 2 CPUs, but if it looks at the ACPI tables and the hardware system has 16 CPUs, it will think that it has 16 CPUs, because we simply don't fix that at all, and we pass the tables as is to Dom0. Another of the problems with the ACPI tables is that Zen can only parse information from the static ACPI tables, because Zen doesn't have an AML parser. AML parsers are big, require quite a lot of code in general in order to implement, so Zen never had. And well, I don't know, maybe that's going to change, but at the moment it doesn't have an AML parser, so it can only fetch the information from the static tables. But there's some information that required by Zen in order to run that's inside of the dynamic table. So the hot block of physical CPUs, the CPU C states, and the sleep states are inside of the dynamic tables, and Zen needs that in order to work properly. So there's an interface from Dom0 in order to pass that information into Zen. So basically Dom0 has to parse the dynamic tables, extract that information, and tell that information to Zen. This is also quite costly because it involves modifying native drivers in order to pass all this information to Zen. And yeah, as I said, it will be possible for Zen to fetch most of this information, but there's one limitation on ACPI, that only one operating system can execute methods. So if Zen executes any ACPI methods, it has to execute all of them, and we don't really want to do that. So it will be possible for Zen, I think, to fetch most of this information, but it will still probably need some help from Dom0 in order to execute ACPI methods. So yeah, this is more or less all the current limitations of Dom0, or the more important ones, and now I would like to speak a little bit about how we are trying to move away from all this and provide a new interface to Dom0. The main points of this interface is that we want it to be as close as possible to native. That's very important because it means that it's probably going to be faster, and it's also going to reduce a lot of the code that we need to put inside of OSs in order to run on top of Zen. If we have an interface that's very close to native, it will mean that the code required in order to run on Zen, it's going to be much more less. We only want to use hypercalls when there's no other interface that we can use. I mean, I'm sure that we'll have to use them from time to time. It's not something that we can get rid of, but we'll try to reduce as much as possible the number of hypercalls that we need to use from Dom0. And finally, we will also like to take advantage of all the new hardware virtualization extensions that came up on recent, well, not that much recent Intel and AMD CPUs. Maybe they've been around for almost 8 years now. So yeah, so regarding the IOM-MIU, that's a very easy problem to solve because on newer CPUs you have what's called the hardware virtualization extensions. On Intel that's BTX, and on AMD SVM, I think, or something like that. And these virtualization extensions basically allow you to create what's called a second stage translation, which means that we can present a physical memory map to the guest that contains memory from different physical regions. We can create a page table, and the guest will think that that page table is their memory map. So that makes it very easy for us to provide transfer and integration. Also, using these virtualization extensions, we can also provide the guest with a virtual memory management unit that's emulated by the hardware, so we don't have to do anything there. And this also allows us to use all the page tables that are supported by the hardware, the different sizes, like we can use 1 gigabyte pages with, well, if the guest wants to use 1 gigabyte pages, it can use them. And basically, we don't need to modify the guest in any way. It's just transparent from the guest point of view. Interrupt management is also quite important. One of the things that we want to do with interrupt management is provide the guest, Dom0, with an emulated local APIC and an emulated IO APIC. The local APIC, sometimes it's provided by hardware itself because there are newer hardware that's capable of emulating a local APIC. That's something, I don't remember the name, I know there's Intel hardware that has this, and there's also AMD hardware that's going to come up later this year that will have this feature. And the IO APIC will be emulated inside of Zen, and we will be using the same code that we already use for HVM guests, so it's not introducing new code into Zen, it's just using the code that we already have there. And finally, we would like the configuration of interrupts to be done using the PCE configuration space, so that means that we'll have to introduce some emulation code inside of Zen. It's not going to be a lot of code, but we'll have to introduce some things, some traps for the PCE configuration space in order for Zen to detect that the guest is configuring interrupts and properly react to this. So here we have another picture of what it will look like if we have a local APIC inside of Zen. The interrupts from the physical devices would still usually be received by Zen on the physical APIC, and then Zen will inject them into the emulated local APIC on the guest. Or I've also added straight arrow from the device to the guest, because if the hardware supports something that's called posted interrupts, it's possible for a device to directly inject an interrupt into a VM. That means that the latency would go down quite a lot because we don't have to go through Zen. The interrupt will be injected directly into the VM. And finally, the problem with the ACPI tables, it's a little bit more tricky to work around, but I think that we found a way in order to solve this. First of all, we will provide a new MADT to Dom0 that will actually reflect the topology of Dom0. That means that Dom0 will see the number of CPUs that it can use. It will not see the number of CPUs available on the whole hardware. Then we will also provide an extra dynamic table for Dom0 that would contain processor objects for these CPUs. This is needed in order to comply with the ACPI spec, because ACPI requires you to provide processor objects for the CPUs on the MADT. And finally, we will hide the native processor objects from Dom0 using a table that's called STAO. It means the status override table, and it can be used in order to hide devices on the ACPI namespace. This table is actually under Zen control, so we can modify the version of this table and we can add new fields if we need to. So as a final note, I think that we can manage to reduce a lot the Zen-specific code inside of the several OSs, especially Linux has a lot of Zen code inside, and we would like to get rid of that because it's quite hard to maintain, it's very different from bare metal, and it usually is, a cause of bugs in general, because most of the x86 maintainers don't really understand the Zen code. They change the native code, and when they change the native code, they break Zen. So we would like to get rid of that. It's easier for everyone. We will have less bugs to fix in Zen, and it's going to be easier to maintain because we will get rid of all of this code. We'll also be able to take advantage of all the hardware virtualization extensions on the market, so that means that we can take advantage of all the newer hardware. And also we'll be able to simplify a lot the Dom0 interface, which means that we can expect maybe new OSs to add support for running on top of Zen, even as a Dom0, because the interface is going to be very, very similar to bare metal. So we expect that maybe someone is going to implement new Dom0s in the future. Yeah, and that's all. I would gladly take any questions now. Yeah?
Are there any plans to go for other architectures other than Intel with these new extensions like ARM or this?
We already have support for ARM. The question was if there are plans for new architectures. On Zen Upstream, we already have support for ARM 32 and ARM 64 bits.
Sorry, I meant these new extensions.
Well, these new extensions are x86 specific, so they don't really apply to ARM. What I can tell you is that ARM already makes use of them because ARM, well, the Zen on ARM port was started very late, so it already makes use of all these new hardware extensions that are present on ARM. And regarding RISC and other architectures, I'm not aware of anyone working on that. If somebody contributes the code, I'm sure it will be very gladly received. Yeah?
I used Zen when it was pre-series, and it was great. It was great because I liked the parameter line. It was really fast. But things have moved on, and now I've forgotten how to do the kernel. So is that still the same process to get a parameter line machine and do the kernel for it?
The question is if you need a specific kernel for a para-virtualized virtual machine. The response is no. Starting from Linux 3.0, all the Zen code is inside of Linux, so you can just build a normal Linux kernel and it will have all the Zen support. That was merged, I think, 4 years ago or 5 years ago, so yeah. So yeah, I think that's all. Thank you very much.